Good morning. My name is Stefano de Marchi. I'm a professor at the Department of Mathematics at the University of Padova. And my talk today concerns this research that I'm involved to since a few years. And mainly my research topic is on kernel-based approximation. And recently, we went through this, for me, is a kind of a new frontier with a different application in many fields that are called the so-called variably scaled discontinuous kernels. And in this talk that I divide in three parts, my idea is to present mainly the basic theory behind this kernel, essentially is a kernel-based approximation, and to provide some applications of this interesting topic. So the first part, we start with some notation. So notation and the general setting, then I present some idea concerning the so-called error estimates for kernel approximation, giving emphasis in particular to the conditioning and the stability of this approximation process. Then I conclude this part providing some information about the strategy for controlling the errors that in a kernel-based approximation, which turns out to be, let's say, particular implementation of a radial basis approximation, is very important, this topic concerning the controlling the error. Mainly based on the so-called shape parameter. But now, so we start introducing what is the main interest of this approach. So we work usually in a d-dimensional domain that we call omega. Okay, here is our omega. Then on this set we pick some points, let's say capital M points that we call centers. Despite the so-called approximation by polynomials, these centers should be scattered in any points of in any places of our domain. So there is no, let's say, constraint in the choice of this center, except for some stability issue that we discuss later. So usually, when we talk about a kernel-based approximation, we start from a function, let's say small phi, which is defined from 0 infinity with values in R. And this function can be conditionally positive definite of some order that we call L, for instance, or can be strictly positive definite. And this also we require some further properties called that the function should be radial. And now we understand more about this radiality of the choice. So there are mainly, but these are not related to, there are many of radial basis function that start from this function small phi, okay, and we divide into, let's say, in two groups. One is the globally supported, and the globally supported one, the most important one, is the so-called Gaussian function, which is a function which is C infinity, as you see. We call GA in the following, and the expression based on a general variable R that usually this R is the square root, so is the norm 2 essentially, is the norm 2 of the point with respect to the origin. So anyway, so you have this function which is the negative exponential, and the L equals 0 shows that the function is strictly positive definite. But there are other family. One other family is called the generalized multiquadrics. The generalized multiquadrics, the definition is this one. Is in this case is you see is a kind of a square root, but is more because here you have a 3 over 2, okay? But the function is a conditionally positive definite of order 2. So this conditionally positive definite, so in general, is related to the so-called polynomial reproduction. For people working in RBF, this is quite common to understand, but I simply introduce the main concept here because I wanted to show you more about the so-called discontinuous kernel, which are for me more interesting for applications. There are then the so-called locally supported. The locally supported I presented to prototype. One is the so-called C2 Wendland function. C2 means that is continuous up to order 2 in any space dimension. Okay, the expression is given again using this R. R for R will be the norm 2. Okay, and the function is strictly positive definite because you see this factor L is 0. Another function is the so-called Boolean function. The Boolean function, except with the Wendland essentially has a so-called polynomial part, but the Boolean function, again, which is a C2 function, has a logarithmic part that you see here. So there is a polynomial part in R, and then there is the logarithm part, which make this function particularly interesting. But there are many other examples of locally supported function. One is called the VU function, the igniting function, and many others that you can build your own. And in the literature, there are, let's say, thousands of radial basis functions that one can construct. But now, we wanted to concentrate in this shape parameter. The shape parameters has a role essentially to localize or to spread your basis functions with respect to the center in which is defined the function. And then the shape parameter has a very important role. So we can read also this way to write the radial basis that you see now from right to left. We can use the following. So the function is a radial because the norm 2 depends on this shape parameter. Usually the shape parameter that we have in mind is has the following role. When epsilon tends to infinity, then the function becomes spiky, so it becomes centered more and more on the center point in which we define our function, okay? And then when epsilon tends to 0, the function becomes flatter and flatter. This is the idea. And so the analysis of the convergence of the approximation by RBF is mostly in the first attempt is related to these shape parameters. Then we can write, as you see, the function in the following way using the so-called scaling invariance of the kernel. So we can pass from a function that you see phi is a function defined in 0 infinity, but we can use a multivariate notation with this big phi that depends on the shape parameter. Then now x and y are still vectors in Rd as it was before, but here we are composing with the two norms, so the value is a real value, but here we have a function in Rd, or we can use this kernel using the so-called kernel notation. So a kernel now is defining Rd times Rd, two values in Rd, which is another kernel notation which is quite common working in this framework. So there is another concept that you have to keep in mind is the so-called native space. What is the native space associated to the kernel? So essentially is the space where the kernel is a reproducing kernel. So it's called a reproducing Hilbert space. It's an infinite dimensional space. okay? And this has a particular subspace that we call the so-called is called the span of the translate, because now using the kernel notation, now we understand from this row that using the kernel notation here is equivalent to use our radial function applied to with the norm to apply to our the difference of the two vectors. Okay. Anyway, using this kernel notation here, you see you have a subspace of the native space. Usually enough native space is a Banach space in the general sense, okay? But this is a finite dimensional because X, capital X, has n components, so the span of capital N functions, okay? And this is the space of the so-called, let's say, is the basis in some sense of our space. There are two other concepts that you have to keep in mind. Another one, the first is the so-called the separation distance. The separation distance between points, between the centers, indeed, xi and xj, defined in such a way, so it's the minimum distance between 2 points, 2 distinct points, okay, and then we divide by 1/2 in order to get the separation distance. On the other hand, for the so-called error analysis, we use the so-called field distance. The field distance, here you have a picture of the field distance. What is the field distance? Essentially is the ball, radius, sorry, is the radius of the ball that you can inscribe in your domain that does not contain points, okay. Another important ingredient is to call the power function. The power function is a positive function, you see it's the square root of something, okay? And is defined in such a way. So you have your kernel at the value 0 minus this quadratic form. This quadratic form where A, if the function is a positive definite, you see your A is a positive definite function, so it's a quadratic function that in some sense represents let's say a kind of paraboloid in some sense, okay? And here the U star that realize the minimum, the optimality of this value are the so-called cardinal function that you can obtain as usual solving the linear systems. The important here 3 examples of the behavior of this power function. This power function for the Gaussian kernel with epsilon equals 6 on a grid of unit points on the left, Chebyshev grid, or Halton point. Halton point is a kind of low discrepancy point that you can use for, let's say, for usually as a test point because they are quite scattered, but at the same time they have a quasi-uniformity distribution. Okay. Then shows, this example shows the value of this power function is very small, and what is interesting is the power function as the number of points increases decreases to 0. So the power function is a function positive that has a limit that goes to 0, obviously fixed the shape parameters. Okay, but one can change also the shape parameters to analyze the behavior of the power function. In fact, here I point out, I recall 2 important results that you can find in this book by Greg Fassauer. This book, the title of the book is Kernel-Based Approximation Using MATLAB. Okay. These 2 theorems essentially are the pointwise error estimate. So the first one says that the pointwise error estimate is bounded by the value of the power function times the norm of your function in the native space. So there is the dependence on essentially on the points on the kernel here, and here the depends on the function f. This is the most important things to understand. And this pointwise error is important for function in the native space. Obviously, there are errors for functions that are not in the native space, okay, but we are not dealing with this for the moment. There is a second theorem that related the previous theorem using the so-called mesh size or the mesh size or the field distance that says the following: if your kernel has a smoothness 2k, symmetric and positive definite, then this, you see, the same results can be rewritten using this h and times some constant here, and then there are all the definition. And also, you see, there is a first part that depends on x omega, the kernel, and then there is another part that depends on the norm of the function, the native space. Okay. How to control the interpolation error? So we have already said that this shape parameter as an important is crucial in the choice of in the analysis of the error. How you can analyze this? Well, there are three main, let's say, procedure. One is the so-called trial and error. Let's say you change your shape parameter, then you compute your error, and then you get your list of error depends on the shape parameter, and then you can decide if the error is minimum, and then in correspondence to the shape parameter that gives you the minimal of the approximation error, then you say that is the best that I can take. Okay. But you can do the same as the power function minimization, because the power function is an error indicator, as I said before. Or you can use a so-called leave one out cross validation that comes from statistics, a well-known procedure. And here I show you what is a typical trial and error strategies. Here the interpolation is the one-dimensional sinc function, Gaussian, with epsilon taken, you see, 100 values of epsilon taken between 0 and 20. Okay. Then we take equispace data points for the kernel, and then you see the behavior of this error in 0, 20 as already the same behavior. So there is a kind of minimum of this error in around, let's say, before 0 and 2, there is this minimum of your error. And then this means that one, looking at this figure, should take a epsilon, which is very small in general, to get the best error approximation. But this is not completely true, because there is a so-called trade-off principle. The trade-off principle says the following, that if you consider the root mean square error, the max error, and the two condition number, so there is a kind of duality between the condition number and the root mean square error. So you see here, where the error is a minimum in some sense, then you get a maximum of the condition number. So the system becomes very Hill conditioning. And so you have to make a trade-off choice between the epsilon that should not be too small, otherwise your condition number goes up too much. And then you have to face a Hill condition system. So the best is to use this trade-off or uncertainty principle that was proposed by Shabak in 1995, that says essentially that you have to balance all the time between the accuracy and the stability, the accuracy and the efficiency in the solution of the system, and the accuracy and stability with respect to the dimension of the problem, because also if you have to solve a system of millions of equations scattered, then you have to consider all this information. And so this is the first part that I conclude here. So now we have all the ingredients that should be enough to understand the second part, which really is the most important part, that present the so-called variably scaled discontinuous kernel. But the variably scaled discontinuous kernel start using the variably scaled kernel. Okay. Then, after understanding all this part, then we go to the applications.